The confusion matrix, our first look at metrics. So metrics measure an algorithm's performance. First, metrics for binary classifiers. Suppose the data has capital P positives and capital N negatives. A binary classifier is a function model, y is a function of x with parameters beta 1 to beta p, that labels an observation as either positive or negative. The true positive means the classifier labeled a positive as positive. A true negative, the classifier labeled a negative as negative. Now suppose the classifier labels lowercase p observations as being positive and labels lowercase n observations as being negative. So capital P and N are counts of actual positives and negatives. Little p and n are counts of predicted positives and negatives. Capital P and N come from the data. Little p and little n come from the classifier. For example, let's look at three extremely bad classifiers. A totally positive classifier predicts a label of positive for every observation in the data set. For example, dog, 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 dog. See, a totally positive classifier is extremely bad because it completely ignores the data when assigning labels. It assigns the positive label to every observation. Therefore, a totally positive classifier, little p is p plus n because everything's labeled positive, and little n is 0. For a totally negative classifier, little p is 0, and little n is the capital P plus capital N. Well, what about for a coin toss classifier? For each observation, flip a fair coin. A probability of heads equals a half. Predict positive if it's head and negative if it's tails. This is indeed a classifier, but approximately half of the data will be predicted positive. So little p is approximately 1/2 capital P, and little n is approximately 1/2 capital N. So these true and false predictions, these are possible outcomes of a binary classifier, true positives and true negatives. False positives, observations that are actually negative that the classifier labels as positive. False negatives, positive observations that the classifier labels as negative. Now our notation, Tp will be the number of true positives, Tn the number of true negatives, Fp the number of false positives, and Fn the number of false negatives. For example, let's look at our extremely bad classifiers. The totally positive classifier predicts positive for everything. So Tp is equal to P, since all the positives are correctly predicted as positive. But Fp is equal to N, since all the negatives are incorrectly predicted as positive. And true negative equals false negative equals 0 because the totally positive classifier creates no negative labels. The coin toss classifier, every positive has a 50% chance of being predicted as positive. Every negative a 50% chance of being predicted as negative. So Tp is approximately 1/2 P, Tn is approximately 1/2 N, Fp is approximately 1/2 N, and Fn is approximately 1/2 P. So let's look at accuracy and error in terms of these true and false. For a classifier that predicts little p, n respectively for data with capital V, capital N actual positives and negatives respectively, little p is the true positives plus the false positives, and little n is the true negatives plus the false negatives. But capital P is the true positives plus the false negatives, and capital N is the true negatives plus the false positives. Accuracy is the true positives plus the true negatives over the total capital P plus capital N. Error, false positives plus false negatives over capital P plus N. Now for a totally positive classifier, that would be true positives is p, true negatives is 0, so we get p over p plus n. The error would be n over p plus n. And if we had a balanced data set, that means our totally positive classifier has an accuracy of a half. So given balanced data, the worst possible binary classifier is one with an accuracy of 50%, 1/2. Accuracies less than 50% are simply dyslexic. If you had a classifier with a 1% accuracy, then just create a new classifier that predicts positive where the other does negative and negative where the other does positive. It'll have an accuracy of 99%. So for example, a coin toss classifier. How accurate will this coin toss classifier be? Well, about half capital P are correctly labeled positive, so TP is about 1/2 P, and about half capital N correctly labeled negative, so TN is about 1/2 N. About 1/2 P plus N correctly labeled out of capital P plus N total, and regardless of the sizes of P and N, the accuracy therefore is about 50% for our coin toss classifier. Here you can see the formula, and A is going to be expected to be 50%, 1/2. You see, extremely bad classifiers are examples of edge cases. They do no better than random in predicting labels of binary data. And it's not unusual for binary models to be extremely bad classifiers. To illustrate, let's introduce a family of binary classifier data generators where both the amount of data and the complexity of the data can be as large as we desire. This is tunable binary data. The goal is binary data whose complexity can range from very simple to classify to very difficult to classify. And we're going to do this using the area under the curve y equals cosine squared pi nu x over the interval 0, 1, because that area is equal to a half for every positive integer nu. Now I'm using nu here, that's the Greek letter for n. So if I take the integral of cosine squared pi nu x dx, then I use a trig identity, and then my antiderivative cosine is sine, but sine at integer multiples of pi is 0, so I just get a 1/2. Here we have nu equals 2, nu equals 4, nu equals 8, and you can see the area of the unit square is 1, and the area of the shaded region is necessarily a half. Now, a point chosen at random in the unit square is therefore equally likely to be either above or below this curve. So the unit square is all points in the xy plane such that the x is between 0 and 1 and the y is between 0 and 1. So randomly sampling, I get points that are either above or below the curve. And points below the curve increasingly stack up vertically as n increases. So you can't spread horizontally when you have a very high value of nu. So the data is going to be points chosen randomly in the unit square, and these are chosen uniformly randomly. Training data is going to have 100 points. The testing data also 100 points. A point xy is labeled positive if cosine squared of pi nu x is less than the y-coordinate. So if it's above the curve, and you can see that if it is above the curve, its y-coordinate is bigger than the curve value cosine squared pi nu x. A point is labeled negative if it's below the curve. The training set, therefore, is about 1/2 positive and 1/2 negative, and the testing set's about 1/2 positive and 1/2 negative. And for large nu, an algorithm is going to have to learn to trust vertical neighbors more than horizontal neighbors. So here we have training and testing sets. So you can see the blue is training and the black is testing. And this is for nu equals 4. So you can see the relationship to the curve now that I've drawn it. So we're going to focus on the test set. Now, our test set, we have capital P equals 52 actual positives and N equals 48 actual negatives. And here you can see that once I put the curve in. I'm going to use a one nearest neighbor's classifier trained on the training set. And then I'm going to score it on the testing set. And then look at my metrics. So here are my predictions for the test set. And as you can see, I have some misclassifications. And that's because of the data in the gray dots here was actually what was used to make the predictions, the training data. In particular, we had 59 that were predicted to be positive, that's little p, and little n equals 41 that predicted to be negative. So we have capital P, capital N, little n equals 52, 48, 59, 41 respectively. The true positives is 43 and the false positives is 16. And you can see the false positives, I've marked them in green. There are 16 of them. The true negatives, 32, the false negatives, 9. The accuracy is the true positives plus the true negatives over the positives plus the negatives, which is 43 plus 32 over 52 plus 48, which is 75 over 100, 75%. The error is 16 plus 9 over the 100, which is 25 over 100, 25% error. Now, here's another example, but in this case we have nu equals 8. And again, using our one nearest neighbor classifier trained on the training set, applied to the test set, I end up with 37 actual positives, 63 actual negatives, 53 predicted positive, and 47 predicted negative. My true positives were 34, my false positives 29, my true negatives were 24, my false negatives 13, and my accuracy was 34 plus 24 over 37 plus 63, 58 over 100. That's 58%. This is getting closer to that random classifier. And in particular, when we go to nu equals 16, our one nearest neighbors is essentially just a totally random classifier on the data. It's not learning anything, and it's not using any information to make predictions. So we tend to use the confusion matrix to organize all this information. So we often arrange the true positives, false negatives, true negatives into a table, so that the sum of the first column is the predicted negatives, sum of the second predicted positives, sum of the first row is actual negatives, sum of the second row actual positives. For example, for our tunable binary data, nu equals 4, we had these numbers. We arrange those into a table, and we get our predicted positives, 16 plus 43 is 59. And then our true negatives, false negatives, 41 predicted negative, and 48 actual negatives, and 52 actual positives. Our accuracy, 75%. So how do we handle all this confusion? Well, these TP, FP, TN, FN, these are useful, but typically we use them to form ratios. For example, accuracy and error are percents. In other words, they're rates. There's some other useful rates. So the true positive rate is the true positives divided by the number of positives, actual positives, also known as sensitivity or recall. The false positive rate is the number of false positives divided by the number of actual negatives. Sensitivity and recall, the true positive rate is the sensitivity of the classifier, an estimate of the probability that a positive observation will be classified as positive. And high sensitivity means there's a low likelihood of missing an observation in the positive class. So the true positive rate is also called recall, because it's the fraction of those observations that are actually positive that are recalled as positive. Now, ideally, our classifiers would have zeros off the diagonal and true positive and true negative on the diagonal. But in reality, the best we can do is small numbers off the diagonal, where this epsilon small in comparison to n and delta small in comparison to p. Now, it is possible for epsilon to be large in comparison to p and for delta to be large in comparison to n. So let's look at an example again. Here was our data, and here's our confusion matrix. The true positive rate, Tp over P, 43 over 52, that's 82% for a true positive rate. The sensitivity rate's 82.7%. Positives are recalled at 82.7%. The false positive rate, Fp over N, 16 over 48, is 0.333. And that's not close to zero. So even though our accuracy may be good and our true positive rate may be good, our false positive rate gives us caution here. It's not close to zero. So statistically, the confusion matrix, here are our variables again. Our sensitivity is Tp over P, but notice that's actually Tp over Tp plus Fn because of our equation for capital P. And so that means we actually have these statistics, or basic metrics. So there's the sensitivity or recall, which is Tp over Tp plus Fn. There's the specificity, Tn over Tn plus Fp. The accuracy, and then these two, which are known as the negative predictive value and the positive predictive value, respectively, but the positive predictive value is also called precision. So let's look at specificity. The true negative rate is the specificity, and the false positive rate is Fp over N, but that's Fp over Fp plus Tn. That's the false positive rate. And now let's look at the false positive rate, Fp over Fp plus Tn. We add and subtract a Tn on the top, and that gives us 1 minus the true negative rate. In other words, the true negative rate is 1 minus the false positive rate. High specificity, the classifier rarely misses negative outcomes, implying that a predictive value of positive is a highly reliable result. Precision, Tp over Tp plus Fp. It's the fraction of observations classified as positive that are actually positive. Compare it to recall or sensitivity. For example, here's our totally positive classifier. The precision is P over P plus N. And if we have balanced data, then the precision is about 1/2. For coin toss classifier, if P is about N, then the precision is equal to 1/4. So for our tunable binary classifier example, our precision was about 72.9%. There's also the F1 metric, and more generally the F beta. Both precision and recall are important. Recall, the rate at which a classifier rates positive samples as positive. Precision, the rate at which a classifier does not label as positive a sample that is negative. And F1 is the harmonic mean of the precision and recall. So 2 times precision times recall over the precision plus the recall. F beta is the weighted harmonic mean of precision and recall, as you can see here. And notice that if beta is equal to 1, we just get the F1 score. Now we can also do this for multiple classes. Suppose the data has labels L1 to Ln. The confusion matrix will then have n rows and columns. And the true labels will be on the diagonal, and the predicted or actual I, but predicted j, will be off the diagonal. So the counts of predicted labels will be the sum of the columns, and the actual counts will be the sum of the rows. So that gives us, in summary, these statistics: accuracy, sensitivity or recall, which is the true positive rate, the false positive rate, specificity, precision, and again recall.